Welcome, ladies and gentlemen, to the technical forum of our group exhibit Hydrogen and Fuel Cells. Welcome to the next presentation here on stage, which will be very interesting because it's about power to gas, microbial methanation, a flexible and highly efficient method. And we will welcome here on stage the head of department microbiology of MicrobEnergy, which is part of Viessmann Group, Dr. Monika Reuter. Please give her a hand.
Thank you very much for the kind introduction. Ladies and gentlemen, I'm very glad to give you some words to the microbial methanation. I want to structure my lecture in 5 topics. First of all, I want to introduce the Viessmann Group and microbiology, which is a subsidiary institute of Viessmann. A few words about the biological methanization, the potentials, the development works and our results, what we have in the lab, and a few words about the economics. Viessmann Group, Viessmann has been founded in 1917. It's a family-owned company with about 9,600 employees all over the world. In red you see all the positions where we are located. Viessmann takes care of all the heating devices, oil or gas based for family, for one family households, but also up to 20 megawatts installed, for example with wood chips or biogas plants. MicrobEnergy is a spin-off company of the Schmack Biogas. Formerly we were the R&D department of Schmack Biogas, and since 2012 we are now an own company. We have 16 people in Schwandorf. One portion of our work is dealing with optimizing the biogas process, and the other hand is the power to gas process. So probably you know the biogas process. It's divided in 4 steps. Hydrolysis, acetogenesis and methanogenesis, so that's the normal process in the bioreactor. And we can see that we have already this process that we go from CO2 and H2 to methane. The biogas normally consists, when you use renewable energy crops, 50% CH4 and 50% CO2. So the plan is to bring extra hydrogen into the biogas process and bring it up to the stoichiometric volume that we have additional hydrogen to produce more CH4. So the methanogenesis is a very old and simple process. So the bacteria, or let's say archaea, it's not bacteria, it's a process which is very stable and it's very easy to control. So the bacteria are depending on the hydrogen and on the CO2, and if they have the gases, they do the work, and if they don't have the gases, they can't work, they sleep more or less. And we have an efficiency factor of about 80%. It's the conversion rate what we have on the chemical process. Possibilities to optimize the biogas process. We have several opportunities where we can put the hydrogen into the process. It can be done into the process directly, either discontinuously. Then we can produce more or less methane, which is or SNG, which is possible to be put into the grid. So we can use the gas grid as an energetic reservoir. But on the other hand, if we don't have excess power in the grid, we can use the normal biogas with a CHP to be burned and to produce power, electric power. What we also could do is that we save the gas, the hydrogen, in an extra tank and make a continuous process to the biogas process. Then we can spare the upgrading unit and produce out of the biogas already SNG, which can be put into the grid. Another possibility is again to produce hydrogen and store it in a tank and use afterwards, after the process, after the biogas process, an extra tank where we use only this specific microbiology and produce also again gas that could be put into the grid. So here we have a slide where we have the two processes vice versa. So we have a technical solution, that's the Sabatier process. The patents are from 1902, so it's an old technology which is already existing for a long time, and it's possible to do that. And well, the pro is that it's quite good to be controlled, and it's easy to, more or less easy to scale up. So there are experiences in lab scale, and it's more or less easy to bring it to technical or to practical scales. The contra or the negative points is that the catalysts used in these technologies are raw materials, so it's depending on where you can find these catalysts, and it's very sensitive. So if you already have some oxygen in the hydrogen, then you have problems with this process. And of course it's a process that runs at more than 250 degrees and overpressure, 20-40 bar overpressure. So it's more or less not so easy to up and downscale the process, also switch on and off. On the other hand, the biological process, it's the methanogenesis. It runs at temperatures 40 to 70 degrees. Okay, there are still some microbes, they grow up to 100 degrees, but maybe we don't use them at the first step. The pro is that we are at low temperature, low pressure, and the microbes are a little bit tolerant, so they can handle with traces of oxygen, where already the Sabatier process has some problems. And it's flexible, and we can use the periphery of a biogas plant, for example, or municipal waste water treatment. They have already this technology, and it can be easily put onto such a plant. But it's a biological system, you have to deal with the microbes. So we see the microbial one is it's a single step, so it's not for big infrastructure. It's more or less regional situated what we plan. And in first steps we think that we could use the biogas plants itself, because we need the CO2. So the biogas plant, as I already mentioned, produces about 50% CH4 and CO2, and is used to produce electrical power. And in times of where there is a need for electrical power, biogas plant can produce electrical power. And if there is too much energy, the biogas plant could produce methane and put it into the grid and work as a storage producer. So these are the two possible operating ways of a biogas plant. Here's some data about the potential. We have about 7,500 biogas plants in Germany with 3 gigawatt. When we calculate with 7,400 hours, we produce about 22 terawatt hours, and we have a storage capacity in average of about 4 hours. So we have a storage capacity by now of 12 gigawatt hours. If we can also manipulate the biogas production, because if we switch to a not 24-hour driven biogas plant, but to a 8-hour, 16-hour driven biogas plant, where the most of the biogas is produced in a certain window, we can already shift it by 9 gigawatt. And if we upgrade it with power to gas, we can shift it up to about 75 gigawatt hours. Therefore, we need electrolyzer power of 20 gigawatt. Here are some results from the lab. Yeah, we shift the biogas. I think the design is a little bit wrong. We start with about 60% biogas, methane content from the biogas, and we shift it up to 95% methane content. We do it in lab scale, so here we have a 10-liter reactor. We are on the way to put it into the first pilot plant. It's a 100 cubic meter plant below. Here we have electrolyzer installed with 20 norm cubic meters per hour, where we can purify up the biogas. So some words about the energy system today. Yeah, this is the amount of energy from nuclear power plants. And yeah, we have 14% of wind power, 3% of hydropower, 7% of biogas. And we will have a change in this regime because we want to switch off the nuclear power plants and bring the windcraft and the photovoltaics more into focus. And we will need a lot of more technologies like batteries to solve the problem of storing the excess power which is produced when the wind blows and when the sun is shining and nobody needs the energy. And we think this is the normal, what we have today, that the energy market is dominated by the big central power plants. So we have a long-term base load, a peak load, and only in the very upper cases we have hourly contracts. And we will see if we have a lot of photovoltaic power or even windcraft. When the wind now is shining, we will have the problem that how to bring the PV power into the night. And this is one solution with the power to gas, that we can do this shift from daytime to night. And using the grids, the gas grid, we can also manage to bring the summer into the winter time. Okay, a few words about the prices. We have already energy markets. So there was an analysis of Regelleistung.net. We have yearly based costs of about 87,000 euro per megawatt and year. And taking this for a pilot plant, what we plan in Allendorf next year, it's a biogas plant which produces 330 cubic meters per hour with a methane content of 53% methane. And this biogas plant is a biomethane plant, so it puts it into the grid, 175 non-cubic meters per hour. Here we want to install a 120 cubic meter hydrogen electrolyzer and want to shift the methane content from 53% to 60%. This is a first demonstration that the system itself works. And when we take the data with the 87,000 euro per megawatt per year and the cost for energy was 1 cent per kilowatt hour, we think that we run the system about 2,000 hours per year, because it's not already there. But if we go further with the change in the energy system, we will have many hours in the year where we have too much power. So I think 2,000 hours per year could be an operating mode. This is the sales price for the methane, 0.8 cent per kilowatt hour. And we have operational costs for the electrolyzer with about 20,000 euros per year. Depreciation time is 20 years. And we think that we get a subsidy of 30%. So we have about 1,000 kilo euros per year. That's about 3%. And we calculate with a conversion rate of 95%. This would be the EBIT for 1 year. So we have about 50,000 euros sales of methane, and for the regulating power we also expect 90,000 euros per year. And these are the costs for the electrolyzer and for the electricity. So we think that we can calculate with an EBIT of 50,000 euros, which makes it more or less economic for this plant. Okay, that's all from my side. I thank you for your attention, and I'm open for questions if you like.
Thank you very much, Dr. Reuter, for this interesting presentation. Are there any questions from your side? Please raise your hand if there are any. Yep. You just introduce yourself, please.
So my name is Anne Seifert. Just a short question for this biological methanogenesis process. So you showed you're producing like biomethane in a biomethane plant, and then you want just to add this additional hydrogen to convert the rest of the power. Is this a separate unit where this, what you showed in the beginning, where like just pure CO2 and H2 are converted into methane? Is this a separate step? Or is it planned to put this H2 to the actual biogas fermentation to higher the yield of methane in the
In that case, it's the hydrogen is put into the fermenter directly. It's not a separate fermenter, it's put directly into the biogas plant.
Any other questions from your side? Are your questions? Okay, now or one more after that? No, maybe not at the moment. Okay, very good. So I understood. Yeah, you put the hydrogen right into the fermenter and produce methane with it. But you could put the hydrogen directly into the grid, couldn't you?
Yeah.
But what is the advantage of changing it into methane?
Yeah, when putting the hydrogen directly into the grid, you are limited. So
that's correct.
Maybe 5% of hydrogen in maximum.
Uh-huh.
But if you have fuel stations in the following steps, then you have about 1.5%, and it's only possible on positions where you have a high gas flow. So you have to be sure that the concentration itself on that point and in the whole grid is stable at below 5%.
Okay, very good. Any more questions from your side? Yeah. Yes.
I think just a technical question. So how actually is this high amount of hydrogen effectively put into the biogas fermenter to really assure availability of the microorganisms for this hydrogen, so that it is actively converted? Because I mean, I don't really know how this works in practice. I don't know, but I assume that this is quite a thick solution of degraded biomass. So mass transfer as such seems to be quite complicated.
Yeah, it's quite complicated. We have different systems, gassing systems for the thicker or the thinner material, and it's very important to bring the hydrogen into solution. So it's depending on the biogas mass itself. If it's thick, we have other technology to bring the hydrogen into solution.
Any more questions from your side? I would like to put another question, because I saw in your calculation you say we have to need 20,000 euro for electricity, probably for the electrolyzers, isn't it?
That 20,000 euros it's for the electrolyzer to keep it stable, to renew the stacks.
But isn't it a good idea to use the electricity from the grid only when it's close to zero, when it's, where there's much to
but at the moment there's
the
not already a model for this, so that's what we can calculate on. But probably there will be a change in the system that we have zero or even negative money for taking off electricity off the grid.
So this calculation could be much better as soon as we get a real smart grid, probably.
That's it.
Very good. Dr. Reuter, thank you very much. If there's no more questions from your side, I would like to thank you all. Thank you very much for your presentation. It was excellent.
Thank you.
And I would like to announce to you the next presentation, which will take place here within around 5 minutes, from Larry Stapleton, Vice President Sales of Ballard Power Systems. It's about engineering services to accelerate fuel cells development. So please stay tuned and have a drink on the house and await the next presentation here in our technical forum. Thank you very much.